Future James here. I thought it was worth just showing at the start of this video what pops out at the end of this video. Essentially we get to a smoothly animated starfield like this. I'm super zoomed in on it so you can see it. But we were able to sort of animate a starfield really smoothly and pretty straightforwardly. So yeah, stick around and see how that happens. On with the video. Hey, welcome back to, I guess this is part 8, I'm losing track, how to look, but part 8 of our series on creating a virtual console with an AI assistant. In the last episode we expanded the debugger out, so we've got breakpoints and we can kind of step through and see where we are in the source code, which is quite helpful and it'll help us write bigger programs. In this episode I want to add support for what's called VBLANK. And on the 8-bits, well, I mean, this is still the case today, often called VSync, but much the same concept. As the kind of system was rendering, you're moving down. If you imagine the old systems with the CRT tubes, as it's drawing pixels down the tube, it gets to the bottom and then it has to return to the top. That space there was a really good time to create graphics in because it would eliminate flicker. You can imagine if you're just writing graphics all the time, you can actually end up with sort of divided frames, frame tearing and flickering because you're changing things as the CRT is moving, as the scan line is moving down the CRT, or your monitor. Yeah, so we're going to introduce support for VBLANK, and that was typically done on the 8-bits with something called interrupts. An interrupt is something that would be fired by the hardware when a certain event occurred, so a bit like eventing in a modern programming language. And we want to implement a VBLANK interrupt, so when it gets to the bottom of the render, we trigger a VBLANK interrupt, and then we've got a period of time in which we can do operations before the rendering starts again. And that, I think it's about 50,000 cycles on our CPU. And we're running at 60 frames per second. This thing's running at 60 frames per second, so it's drawing those frames 60 frames a second. And to support that, we've got about 50,000 cycles between renders. And in there's where we'll do a lot of our graphics handling. Now, my original spec was based around a polling approach, and I ummed and ahed about this at the time. Essentially setting a flag in memory when we've reached the bottom and polling for that in our game loop. Which is really easy to do. It's really kind of beginner friendly, but it's not really optimal. It wastes a lot of CPU cycles, and it's not how the 8-bits really worked. The consoles worked, and yeah, I decided I wanted to make it a bit more realistic. So we're still going to support polling because it's simple for people, but we're also going to add in a typical interrupt. So and basically an interrupt, a sort of hardware called interrupt, you would basically say enable the interrupts on the hardware, that'll tell the hardware to send the interrupts, to call the interrupts. And then you'd register, will register pointers in memory to our code so that the CPU will look up the pointer when an interrupt is fired, it'll look at the pointer and call the code that that's pointing to. Essentially a callback when the VBLANK fires, and there we'll do our rendering. So in that, let us just look at what I've changed. I've changed the 2 spec files basically. So I've got the git diff up, new version on the right. I'll just pull this over here a bit so we want to focus on the right. I've added a new flag, which is whether or not the interrupts are enabled. That's in the flag register. And it's enabled by 2 instructions, SEI and CLI, which we'll see in a second. They were already in place, but we didn't really do anything. Okay, just a bit more noise, Yes, set by CI, clear by CLI. You return from an interrupt by calling RTI at the end of your interrupt handler. That's all pretty kind of traditional 8-bit stuff. I can't remember what it was on the 16 bits. I think I said at the first episode I started my career writing C and 68,000 assembler, but I can't remember any 68,000 assembler at all. That's completely left my brain. Yeah, so document the opcodes, RTI, documented SEI as you can see there. A little bit on how it works. Frame budget, that's for 50,000 cycles per 60 Hz frame. and a bit more information on the interrupts, where we store the interrupts. So that's the pointers. So that's the handlers, the callback handlers. We're going to implement a scanline interrupt as well. Where if you remember the memory map at the start, we talked about that a little bit, but we'll revisit that when we do it. Yeah, and then when and how do they fire? Yeah, so we've done that. We've got some example code. Just fleshed out the spec really. Similarly, memory layout has just been updated to correspond. So there's our address pointers, our handler pointers, and again we had some sample code in for polling, and now there's some sample code in for using the interrupts. So just to give the thing some context. So hopefully that's enough information in the specs for the system. I have also, because it would be a bore with me to write, we're going to take a slightly different approach to this, just because this is another technique I use, and I've not done this so far, is I'm going to ask Claude to give me a suggestion as to how to implement it before it does it. So I've given it the specs, I've given it the code in this prompt, and I've basically said, propose a solution for this. So we will see what this does. Launch Claude. I have half an idea what it'll do, because I can again imagine the implementation. It needs to update the CPU file. I think I would you could trigger the interrupt from the CPU or the renderer. You'd have to count the cycles in the CPU. We know how many cycles are per frame, but I'd be slightly wary of that getting out of sync on an emulator from the actual renderer loop. So I think I would put it in the render loop, where we have quite precise timings as well. And it's really the renderer that we want to trigger this thing. So I think that's where I would put it. Let's give it a run and see what it does. Let's see what happens. You have to excuse me, I'm still a little bit under the weather. I don't feel as bad as yesterday, but I still don't feel great. So if this is confusing, I apologise. I don't think it is so far. I don't feel quite as brain fogged as yesterday. Let's see how it goes. Let it run away. Excuse me. Oh. Yeah, I'll snip this out if it takes it a long time. It shouldn't take it too long. At some point in one of these spaces, I'll start talking about the weather, which is obviously a very British thing to do. And by talking, I mean complaining. Okay, great. Didn't take long. Let's have a look. Let's see what it's told us from the top. Okay, VBLANK interrupt needs CPU, check for pending interrupts and dispatch them. Yeah, memory bus. Handle int status, right one. Declare semantics, yes. Set VBLANK at 60 Hz after frame completion. CPU coordinate timing between CPU execution frame. So let's look at what it's actually proposing to do. So implement the SEI, CLI, that's pretty straightforward. Check for interrupts, so step, it's added check for interrupts. Okay, so that's a new thing. Add interrupt dispatch logic, so it's just going to read the addresses. Yeah, so if the interrupt is set and the interrupt handler is enabled, then dispatch the interrupt. That all looks fine. Dispatch the interrupt. Okay, this is, we have to manipulate the CPU registers, push things onto manipulate the program counter and push the return onto the stack. So when we RTI from the interrupt, we can come back to where we were. Things stay as they were, rather. So we can come back to where we were. The interrupt will fire at the end of an instruction that's already running. So our actual code could be in like a polling loop, for example, perhaps updating some AI or enemy positions or something like that. And midway through that, the interrupt will fire, will end up somewhere else in code, will render the state based on the code. We'll do our rendering based on what else is in memory. Memory will return, and the program counter needs to go back to where it was so that the instructions can continue. And they're called interrupts because they interrupt things. Which that's why I think they're called interrupts. I've never actually looked at the official definition, but that's what always made sense to me. Okay, so pretty basic stuff. If we update that place in memory, then we need to do the right stuff. Web GPU render integration, set VBLANK. Okay, it's setting the VBLANK ready essentially in the renderer using our shared array buffer, which is what we want. Okay, interrupt fire, create a snapshot. Okay, so after the error message, do we actually want it to do that? I'm going to let it do that and see how it integrates that. I'm not quite sure how it's going to integrate that, but the rest of it looks pretty sane. So I'm going to let it do that, and I'll inspect this code basically. A test program, right, assembly test program to verify interrupt handling. Okay, fine. There's our handler. So here you can see it's registering the handler. Okay. Did I give it the assembler? I did give it the assembler, okay. Okay. Do back work here. Yeah. Okay. Okay. Yes, that's let it go. Pardon me. Oh, say still a little bit under the weather. Okay, we're done and we're back, and I'll probably cut that out. We will. I've probably cut something out, I should say, if you're watching this, because it took a little while. It took I think about 6 minutes. Anywho, let's see what it's done. Let's close our spec diffs down so we can see our screen. Should have updated the CPU. Let's do a diff. We don't need to do a diff. It's really small changes, really. Okay, there's one change. It's set the flag constant, fine. It's added check interrupt in the cycle, and down the bottom it's added the check and dispatch, fine. Exec SEI, exec CLI, exec RTI has been done. Okay. Okay, let's see the next one. I just want to see its implementation. Okay, fine, that's correct. Just setting the flags. Great, that looks fine. Let's look at the memory bus. If you can see it, I can find the changes through the little green highlight in the right margin, and in the left margin there's a big bolder one when you're sort of looking at that bit of code. So if we, yeah, okay, so that's just making sure that, if you look at the spec, it's write one to clear, lets you remove a bit, and it just makes it easy to clear selective interrupts, basically that pattern. It was a typical pattern on the 8 bits, but that's right, it's not a normal memory write, we do the write one to clear. Otherwise you kind of have to invert it to clear, if you see what I mean. If you want to set 0 to clear, you'd have to kind of look at the flags, compose a bit pattern. You can see it'd be awkward with a bit pattern and the bitwise logic. But writing one to clear, you can just set that 1 bit in the byte, write it, it clears it just that 1 bit, and the zeros don't do anything. So it's a common pattern. Let's look at the renderer. Okay, it's just made this change here, which is to set after rendering, is to set our interrupt to 1, enable the interrupt. Okay, I think what I might do is extract some of these constants. They're a bit spread around, so now we're introducing the hardware registers, the special areas of memory that map to hardware now. And I think what I'll do is pull those out either into the memory bus or into like memory types so that they can be shared across the project. It's not great that they're getting spread around. and then we can feed that into our guidelines. This is where you map hardware registers. I probably won't do this live. I'll do that out of here because it's pretty tedious, right? Okay, so that's that. Does it change anything else? I don't think it's changed anything else, is it? That's probably it. Web GPU rendering. Look at the console. Yeah, okay. Let's see if it's working. See if it's doing anything. We might have to pick up some sample code. Well, it's not doing anything. Let's grab our smiley first and make sure our smiley still works. So I didn't say the last thing, but I've started to put the examples in here. So VBLANK minimal. So I didn't actually tell it about that. That's good. I ought to expand the README out to include that. But it's added a README for the samples and a smiley 2. Well, smiley 2 is my sample. So let's start with something we know did work. Okay, so if we were to assemble that, go to the console, run it. Okay, so we've not broken anything. Hurrah! We can run quite complicated programs. Let's look at what these examples are. I mean, it's created this file. So it's describing the examples it's created for us. That's great. Okay, it's given some guidance as to what these things do. Okay, let's have a look. VBLANK minimal. Let's load it into our assembler because that has syntax highlighting and WebStorm doesn't. We've got a better environment than WebStorm now for doing our assembly. Okay, we've got some errors. But I was eyeballing that in the code. I should have given it the assembler.asm. That's not how we can't give. It's trying to give it the high bits and the low bytes of a label. And that's not how we do that. So I'm going to get it to correct it. I can't remember what we wrote in the assembler spec. But what I'm going to do is give it these two, because this will be the same. I would imagine this is going to be the same kind of, same error. Because I didn't give it the spec for the assembler, it's kind of just pulled, I think, on training data on other assemblers it's seen. So we're going to give it these two samples and give it the assembler spec. And what we're going to say in Claude is to load the here's the spec for the assembler. Can you update them? So I'm just going to grab the no, I didn't do it. Press escape. Let's go again. My bad. Let me just grab the assembler spec. I'm just going to paste it in here. Tools, assembler. Just grab that. We can just pop it in there and see what happens. Go to update the samples. I realise I probably didn't. It knows where the samples are from existing context. And that's one of the nice things about keeping the context window going. We've talked about resetting it, restarting it. You can see it's now read the assembler spec. So that's an example, I guess, of me giving it incomplete information, and that's one of the dangers of kind of the code generation approach of the LLM is if you give it incomplete information, it will fill in the blanks from its training data and its rest of its context. And the problem with that is, it can draw on concepts that sound very similar, in fact are very similar, other assemblers, but actually have different subtle differences. And you can end up with errors as a result. So that's kind of an example of how giving an incomplete spec for a concept that's it's encountered in its existing training data can go a little bit wrong. So you need to be careful and wary of that. Let's go back and load our revised code. We've got more errors. Interesting. I don't think we've got a right shift. I don't recall specifying a right shift. We might need to update our assembler, which is interesting. Because when I wrote this, I didn't have the concept of the interrupts. I think I forgot to update the assembler. Yes, I've basically not updated the assembler to account for us wanting to load these things into pointers. We've got pointers where we've got the labels, dot loop, jump loop, but that's done through symbols, and we need to be able to get one of those markers, one of those labels, and get it into the pointers. And because I didn't have interrupts when I put pointer interrupts when I put this together. There's nothing really in the assembler to help us with this. I don't think we've got we have got a shift right, look. It's not worked. That's interesting. I don't remember doing this. So why isn't that working? Let's see if it actually. It might actually. It doesn't. It does. Of course, because the errors are coming from the assembler into code. So there is a problem with our assembler. Interestingly. Let's go into code and see if we can fix this through the LLM. So let's do a new file. So I'm just going to give it again the spec for the assembler. Copy path reference, absolute. Then I'm going to give it the actual assembler code, which I don't think it's looked at. Okay, it's our code. We're going to grab our error from VS Code, not from Monaco, not quite VS Code, but we could load all that into VS Code. It looks like can you check both and for issues. Dawn as well. We have written tests. So let's also look at the tests. I couldn't have written tests for this, but we had. And let's see if we've got a test in here. Well, we will have a test in here for this. Interesting. We don't have a test in here for that. Interesting, we don't have any expression tests in here. Okay. We also have missing. I must not have reviewed that file. Escaped my review. I don't remember it being generated, to be honest. I reviewed the assembler. I didn't review the tests. That's on me. I screwed up there. I think I was kind of focused on trying it out, and then I've obviously just lost track of the test file for it. I'm going to do this I'm going to leave this context running in case I decide this context is useful. What I'm going to do is actually, let me make this bigger again. I'm actually going to create another context for Claude, and I'm going to I'm just giving it another couple of files to read. I wanted to also have a view of our guidelines. I'm going to give it another context to fix this, because I think this isn't related to VBLANK really. This is related to our assembler, and I don't think therefore the VBLANK context is particularly helpful to us. So let's pop that in there. And this is again one of the sort of part of the craft, let's say, of using these tools is understanding when to use a new context, when to use an existing context. And really, the problem is if the context gets too big, well, the bigger the context is filled with data, the more likely is the LLM will go a bit wrong. And my sort of simplistic way I sort of mentally think about it is like as a possibility space, an ever-growing possibility space. As these things are predictive machines, so as the data it has to predict from gets bigger, the range of predictions gets wider, and so it's more likely to deviate from like the acceptable set of predictions that run down the middle of this spreading out triangle. It's just simplistically how I think about it, and it's how I kind of nudge myself to think about context. I think about it like that, just a sort of simple mental model. Okay, so it thinks it's done it, but what's quite interesting is over here, I am seeing a compile error. It's just unused. Interesting. Let's just have a search for. I guess it's probably it's assembling, isn't it? It's just not looking for jumps for the ops in the output because it's testing in different ways. Okay. I think that's fine. I'm going to come back and look at that because I don't particularly like having that like that, and I don't like the magic numbers in the tests. We've told it not to use magic numbers already. It's not listening. It's not listening to that anyway. In any case, I'll come back to those things. It seems okay. Let's look at the assembler now. We have to refresh this, I think. Yeah. Okay, that's our sample. Okay, our assembler now has no errors, and we're loading the stack, the pointers in, installing the interrupts. Okay, that's the low byte, so just add it with the lower byte, the lower FF, and then to get the upper byte, we shift the high byte down into the low byte. Yeah, so that'll work quite nicely. So finish part, clear screen to black. Main loop, see. Cool. Seconds. Okay, so this thing is going to basically update the screen in the VBLANK. Let's see what happens. Slightly nervous of this. Assemble it. Yeah, that's not worked. I didn't think it would. I don't think the VBLANK is wrong, but I think the assembler is wrong. What I'm going to do, I'm not going to poke with the assembly here. Only because I'm going to do it in a way that I want to talk about in the next episode, which is going to be really exciting, and I don't want to ruin the fun, basically. So I want to pause this recording, resolve the assembler, and then we'll see where we're at. But I think the VBLANK's working. I don't think it's a VBLANK problem. I think this is a problem with the way it's this code here. So I'll go and fix all this, and I'm back in a few minutes. Hail, back, debugged. There were a couple of problems with the assembler, which are just noise really and not that interesting. However, there was a far more subtle bug which took me a little while to figure out. If you look at the assembly code, we're doing things with a stack. So we're preserving registers when we go into interrupt and restoring them. And at the end, we've got this RTI, and that returns from the interrupt. And that does a few things. When we dispatch the interrupt, we have to preserve the status of the flags, and we need to add the interrupt flag on here, which we'll do in a moment, and we need to push onto the stack the place to return to, which I think we talked about earlier. And there was I noticed that we were ending up in strange memory locations, which you would get from invalid opcodes. It's reading random RAM. The opcode structure no longer makes sense to it, and I was getting errors, random opcode errors popping out. And when I kind of stepped through it, I use this system to step through it for the most part. Quite, I mean, obviously it's quite subtle, lots of bytes and stuff. It'd been very boring to watch. Maybe if this was like a live stream, it might have been interesting, but it's definitely not a YouTube video you want to watch. But that order I mentioned is really sensitive. You have to get the stack just right. And there were a couple of things wrong. Its clear screen implementation originally had messed up the stack, so I corrected the stack in the assembler. That was straightforward, and then clear screen worked. I made a slight change to clear screen code to simplify it too. What had actually gone wrong was in exec RTI. So when we run the RTI, we pull the address we need to return to from the stack, and we pull the status flags on the stack. The issue, and that's the correct order. If you look at dispatch interrupt, which is what actually caused the interrupt, we push the status flag and we push the high and the low bytes of the address we want to return to. The issue was that this thing was here, so we'd end up with essentially a mangled pointer to return to, and obviously status flags that were completely wrong. The orders have to match really carefully. So this was not something that the LLM could find or really help with. At least I had a go at asking it, what do you think's wrong, and it wasn't really coming up with anything very useful. So it was a bit of a more traditional step through, put things in the console log. That kind of more traditional, shall we say, process of debugging it. Just checking I am recording. I am recording. I'll just make sure I have restarted recording. Yes, so that was a little bit painful. But expected pain. Not surprising. When we did the CPU, and as we make changes to the CPU, it is quite subtle. I think the LLM's doing a pretty good job on the whole, but they are not perfect. Neither are humans. A human could have made that mistake just as easily, and we'll have to pick up on these things. Sometimes you can pick them through code review. That was really subtle. I did review this. Well, I didn't review the RT. We had a look in this video at the output, and it looked broadly okay. But I hadn't done my off-screen review yet. And what I'll peg for my next off-screen review is to look carefully at the branch and jump calls and the stack management. Make sure any push in the CPU implementation is matched by the appropriate pop. It's really key. Oh yeah, so with that done, I've reloaded our assembly in here. Let's go to the console. We can compile it and we can run it, and we'll get a flickering. It's cycling a palette basically in the interrupt. So our interrupt's getting called. It gets a palette, and that's happening inside the vertical blank. It's also writing a little white byte to the top left, which it's hard to kind of see, but top left is a little white byte which writes as well. So that's, I think, quite interesting. I'm just going to pause that because it's going to get mess with my eyes. So quite interesting. At the moment now we've got a working interrupt system, which is great. We can do interesting things with that. I'm just going to commit it. This is from our expression bugs earlier. Let's just commit our interrupt work. Yes. So hopefully you agree that's fairly interesting. We do need to put the flag on here, the I flag. I couldn't see that when I was doing the debug. I didn't need to, and kind of knew what was going on with it, but it would be helpful to understand the I flag. So we will use Claude. I used Claude in the end to fix the RTI thing because I wanted it to also fix the tests. So you can see the prompt I gave it was having sort of diagnosed the issue myself and tried a few things. I basically said to it, okay, story errors. I think the problem is an dispatch interrupt to next RTI. Tell me if you disagree, but I think the push and pop orders are incorrect. And right, also update the test for the CPU as well as fix the code, which it went off and did with that nudge pretty straightforwardly, all fine. Fix the tests, acknowledge where the mistakes were. Great. The next thing I wanted to do is, I say, update this flags thing here. So let's just go to the debug view. Let's get the debug view path, source, dev kit, source, application, debug view. Okay, is it the debug view we want? It's the register view, isn't it? We want to update the register view. So let's get the absolute path. Can you update the status flags display in register view to also include the I interrupt flag? We want that updating. And saying well, it does that. Say I'm putting a tackle just outside of videos, because I don't think it's particularly interesting to watch, is we're using a render loop to generate the interrupts. And interestingly, it hadn't occurred to me before, but when this component isn't mounted, as it were, when it's not when the canvas isn't there and running, there's nothing to generate the interrupts. So if you're on the debug tab, you don't see any you don't get any interrupts fired, which is not really what we want. So I am going to do a little bit of rework, possibly to use the sort of the hide stuff rather than the unmount. At the moment, we're completely unmounting React components, and I think what I might do is just kind of make it invisible, or I'm just wondering if that also triggers request animation frame. I'll have to check. But basically, I will rearrange things so that we can have the interrupt running and see the console while the debug's running. I think what I'll probably do is actually mount. I mean, at the moment, it looks like there's not a lot of room because it's super zoomed in, but actually, you know, from a like, this is me using it with my normal resolution, there's tons of room on this dev kit. So I might have the console view running alongside the debugger, so you can see the visual and the hex at the same time. I think that would be helpful. Interestingly, while we've been doing this, it's added the interrupt flag. Great. That's quite funny. It's just included that. Great. Thanks for that. Let's just reset things. Yeah, it says no, it's not set because there isn't an interrupt active. Great. So yes, we should be able to. Well, slightly awkwardly, as I said. So if I was to assemble this, and I'll just put a breakpoint here, run it. If I put a breakpoint in the VBLANK handler, it won't get hit. So now things are running, but it's not getting hit. Just take that off, press run. It's not getting hit. If I move over to console, interestingly the iflag, let's see if the iflag works. And now it's hit. Great, because it's got a render loop firing. Interestingly, the iflag is not. I'm trying to remember, does the dispatching interrupt clear the flag? I have to check. I kind of thought we'd be able to see that, and we can't. But you can see you can debug. I'll double check the exact behaviour of the iflag. I can't quite remember that little debug loop has thrown me a loop. It was quite complicated. Lots of hex addresses and tracking through because the stack was wrong. Things were getting pushed out, and it made for quite a complicated mess in my head. Which is kind of like the old 8-bit days. I've just refreshed my memory on the interrupt stuff. Yes, so that flag indicates if interrupts are enabled or not, not if one is firing. That's in the memory map. If one is active, and we can poll on it. So it's whether or not they're enabled or not. And I've just set things up with a breakpoint before SEI. So SEI, CLI makes sure the interrupts are disabled. They should be disabled on a reset, but it's kind of good practice to make sure they are clear. But then enable interrupts in CPU, that's what the SEI will do, and that should turn the flag bright. The reason and then when we hit the VBLANK handler, it will go back to disabled. And the reason is that when the interrupt is running, interrupts are disabled, so an interrupt can't interrupt the interrupt. That would be kind of weird. So if I was to run this now, we should find it's grey. That's what we want. Grey, step over, it's now active. if I just take that breakpoint off, well, I'll leave it on actually. Let's go to the console. It's going to be slightly weird because of this render loop thing, but if I now run this, well, I'll take that off a minute so we're going to cycle through there for a while. Right, so we now have a VBLANK handler. It's grey. If I put a breakpoint back in here, let this thing run on, we're back in the main loop. It's enabled again because we returned from the interrupt. So you can see that working. Hey, I went kind of off video for a moment there just to create a couple of examples that I thought might be useful to show the VBLANK in action and the benefits of it. So I've essentially created an animated Starfield. So let's just get the basic version up. So I've created one which doesn't use our VBLANK. Oops. So this one I created here. We'll have a look at it in a second. This doesn't use our VBLANK. So if I assemble it and run it, you can see it's quite. Hopefully, you can see it's quite flickery. Not great, and that's because the data is updating while our render is occurring. So we end up with stars not there, stars there, stars in both positions. Just the timing's all over the place. Not great. So we can use our VBLANK to smooth that out by making all the updates to the screen inside the interrupt, inside the VBLANK interrupt, while our system is moving back to the top of the display. If you recall, we have about 50,000 cycles to do work in there. So here's a version of this, much the same, but just reworked to use the VBLANK. Oh, I should have reset the console, really. Reset the console. Okay, let's assemble it and run it. And hopefully you can see now how much smoother that is. It's really smooth. There's no flickering. It's using our interrupt to perform the updates in the background, which is pretty cool, I think. That's the benefit of the VBLANK interrupt. A good question might be, that probably took me about an hour to create those examples for our console, and really they're just updating the frame buffer. And to get there, I basically created a few things along the way. So I took our smiley, created a draw pixel. I created a static Starfield, which just uses our draw pixel to draw the stars, and the stars are all at the bottom, kind of loaded into memory using our kind of assembler loading pattern, where you can reserve memory and pop random bytes in. And then finally, I moved on to the animated versions here, which essentially include the animation code to move things right to left, which is very straightforward because we just need to move things on one line, left to right, and it's 128 bytes per line. So yeah, it's pretty simple arithmetic. I've kind of laid out the screens to be, this screen in particular, mode 0, to be fairly friendly to doing this kind of stuff. I think it's the screen people would use the most in the console. In any case, a question might be, well, that didn't take long, James, and that's because I cheated, and that will form the basis of our next video. I cheated the hard way, and in our next video we'll go through how I cheated, and we'll look at how we can cheat the easy way, which I think is going to be really cool. I'm really looking forward to recording it, and I'm really looking forward to sharing it. I think it's super cool, and I think it helps demonstrate, well, the fun of this project, but probably more importantly, it shows how you can integrate AI into kind of really custom, unique scenarios without too much difficulty. And I think that hopefully is really useful to a bunch of people. So that should be a sort of big episode. I'm looking forward to it. But with that said, I will wrap things up there. That's a real high point to leave it on, I think. And yeah, great. Thanks for sticking with me. Hopefully things are getting more interesting now. Things are happening on the screen. We can do stuff. It's getting more interesting. And the right to left Starfield, I suspect the first game we create will be a really simple side-scrolling shooter. So that should be really fun and cool. Yeah, great. Let's leave it there. Thanks again.